then the absorption happens. It's called resonance absorption. Okay. Now, when we say electromagnetic spectrum, there are a bunch of waves, starting with the radio waves, microwave, IR, UV visible, X-ray, gamma ray. But as I said, common man, when we say light, that is coming in the visible part. So today's talk, we are confining to UV and visible region, which is essentially from 10 nanometer to 400 nanometer is a UV part, 400 to 700 nanometer is a visible part. That is a WIIM or part we talk about, whatever visible light. That is a frequency range. Now, in terms of, if suppose you want to measure how much light is absorbed by a molecule, an instrument called UV visible spectrophotometer is used. Many of you must have used it, but some of you did not use it. Essentially, it works on the principle of transmittance. See, light is falling on a molecule. Red. What does it mean? Green light is absorbed. So by measuring transmitted light, what light is absorbed. That is the principle of this UV visible spectrophotometer based on the transmitted measurements. So they use two different types of lamps. One is a deuterium lamp, another one is a tungsten lamp. So deuterium lamp is, there is a holder where you have deuterium, which is isotope of hydrogen. Deuterium gas will be there. And there is an arc. The arc will basically excite this deuterium from this ground state to the excited state, like the way here. So deuterium will also have energy levels, electronic energy levels. During the arc, using the arc, you can excite deuterium from the lower level to the higher level, and when the deuterium emits light, it comes in the UV region from roughly around 200 nanometer or 190 nanometer to 300 nanometer range. So using that light, deuterium can provide ultraviolet. UV means ultraviolet radiation it can give. This tungsten lamp, which is basically working on the principle of black body radiation, in the sense that there will be a tungsten material, you pass electricity through that, it becomes heated because of the resistance, and any body which you heat to maybe 1000 or 2000 nanometers. So that is the entire, it covers more than visible and IR region. So this is the two light sources in a UV visible spectrophotometer. So the light is generated, it is coming through, there can be filters. Using that filter, you can probably allow certain wavelengths. And there can be even better way of selecting the wavelength by something called a monochromator. Monochromator is basically a piece of metal with a lot of fringes. What happens is that when the light falls on these fringes, refraction happens. Exactly like a light waves pass on a prism, it gets dispersed, right? So like that, this is a kind of a prism called monochromator. You can rotate, it will be standing on a motor. Motor can be rotated. Based on the rotation, you can select any particular wavelength. It will be dispersed, and from this dispersion using a slit, you can select a particular wavelength for excitation. Suppose your sample is absorbing green. So you can use a 500 nanometer, 500 to 510. So basically you can select a particular wavelength using this monochromator. Then it goes to a beam splitter where one part of the wave is gone through a reference part and another one is going through a sample part. So this container, it's made of probably quartz kind of a material. It is called QH. So those who do this UV visible spectrometer or fluorescence spectroscopy, they are familiar about this word. It's called QH, which is the container. You take a solution sample here. You can actually take in all kind of states of matter, solid, solution and gas. But for UV visible, normally people do in solution. Now, whatever solvent you are using here, you take the reference only solvent without your sample. So the only difference between reference and sample is this contains your compound, but this doesn't contain your compound. Now, light pass through. Here your sample absorb light. Whereas here, What will absorb the light? There is no sample. Then why are we using that? Suppose your solvent is absorbing, right? So you need to differentiate the absorption of your sample from the solvent. So as a reference, we use this solvent alone here. So this detector will see if at all solvent is absorbing, detector will detect that. Detector can be a photodiode, which is basically a PN junction, or it can be a photomultiplier tube, which depends upon a photon falling on the detector can generate a current, right? So based on that current, you record wherever there is an absorption, the intensity of the transmitted light will change. So you are measuring the absorption based on the intensity variation of the transmittance. That is the principle of UV visible absorption spectrophotometer. Wherever the intensity of the transmitted light changes, the recorder will record it, and this is what you call as an absorption spectrum, right? Based on that, wherever your compound is absorbing, you have the sample absorption and the reference subtract that, so that whatever solvent absorption is getting eliminated, you will get finally only what sample is absorbing. Now, a few terminologies you are supposed to familiarize if you are dealing with the UV visible absorption spectroscopy. One is something called signal to noise ratio. What is that? Signal is something that you know, this is what your signal, which represent the absorption process. What is noise? Yeah, unwanted waves. So how does noise comes in a spectrometer? What is the source of this noise? Radiation? Impurities. No, it's not about your sample at all. This noise is not due to your sample. Signal is due to the sample. Noise is mostly coming from electronics part, the random disturbances from the thermal movement of the electrons in the detector, or from stray light, not the light that is you use for exciting the sample. So there are multiple reasons. Random fluctuations in the electronics can generate some kind of a peak, which is not due to your sample. That's called noise. So noise will give you misleading information. So it is very important that your signal is much more intense than noise. That is why signal to noise ratio. So if the noise should be less than the signal to noise ratio should be high or low? Very high. So 10,000 to 1, right? So like that kind of a variation difference should be there between your signal and the noise. Then you are getting supposedly a good spectrum. So any instrument that you are buying, first time you check it, signal to noise ratio. That's very important in getting reasonably good signal. Another important aspect is resolving power. Suppose your sample is absorbing very closely, 500 nanometer is absorbing, 500.5 nanometer is also absorbing. There are two different transitions. You want to see these two different transitions as two peaks. What you need is a spectrometer with high resolving power. The resolution of how much small nanometer it can scan part by part. So that is called resolving power of a spectrometer. So adjusting the what do you call it? We said initially we said monochromator, right? Monochromator fringes. Suppose there are more fringes, then the resolving power will be more. And adjusting the slit width. Slit is an opening that is coming through, which allows also a bunch of lambda can go through. The slit width is high. So adjusting these things, you can actually increase the resolving power of a spectrometer. That is another important aspect in measurement. Otherwise, what happens? There are peaks which are coming very close. If your resolving power is less, if the instrument resolving power is less, it appears as one peak, right? It could be actually two peaks if the resolving power is high. So that is one aspect. Another one is width of the spectral line. See, we talk about UV visible absorption. So in this UV visible absorption, as we said, the energy gap we are talking about is electronic. That means the electron is the one that is going to interact with the photon. You have molecule, atoms, nucleus, electrons. Electrons are outside, and photon is the one that is getting interacted and the energy exchange is happening. So the electronic energy is getting perturbed when light, you are shining UV and visible interaction. So when the electronic energy is getting perturbed, supposed to get a transition from a lower electronic energy level to a higher electronic energy level. That means you are supposed to get a line spectrum. One transition is one line. So the question is, why are we getting a broad spectrum? Now, solution spectrum, if you take, there will be a width of this spectrum, absorption spectrum. So where is this spectral width coming? That is the question. There are many reasons. Main three reasons are Doppler effect, uncertainty principle, collisional broadening. So we need to probably work on these things to minimize the width. Out of these three, one thing you can do anything, uncertainty principle, that is a inherent condition. It has nothing to do with your instrument. But the other two things probably you can work on, Doppler effect and collisional broadening. What is Doppler effect? In physics, you must have learned about Doppler effect in terms of sound. A train is approaching you, the horn becomes louder, right? So same thing happens in light also. When the light source moves, then there can be perturbation on the frequency. You have to imagine that there is a source, assume that it is standstill, okay? It produces a wave. Now it moves also. So it is propagating a wave and at the same time it is moving. What happens if you are observing that? Instead of getting a signal in one type of signal, there can be many signals going to be superimposed. So it appears to be there for the detector that the frequency is getting changed. So frequency can change, intensity can vary. So all these things are contributing to something called Doppler effect. So as a result, the detector which is detecting this wave will see that it is not just one. The frequency means energy, it is changing, right? Spectral width is enhancing. Uncertainty principle is a very complicated situation here in the sense that normally you learn uncertainty principle as delta x into delta p greater than or equal to h cross by 2 pi, right? Position and momentum, uncertainties. But here it is not about position and momentum. They are called conjugate variables. Any conjugate variables can provide uncertainty principle. Here it is time and energy. So the error in time, measurement time, and the error in energy, right? These have a uncertainty relation. The more error in time, the less energy uncertainty will be there, or vice versa. So something which is remaining in the excited state for less time, then the energy that you are measuring, which is the emission, will have more error. So that is going to spread on the x-axis is basically energy. So lambda is energy. So that spread will be high because of this uncertainty principle. That is another aspect. Collisional broadening. So in solution, which phase it will be collision will be more? Solution, gas or solid? The immediate answer may be gas, but actually the answer is solution. Because gas, what happens? It spreads out. So the probability of collision will actually be less in gas. Whereas solution, you are actually confining it and allowing movement. So the probability of collision will be very high. That's why in solution spectra, the collision leads to broadening. How collision leads to broadening? So things are colliding to each other. So when they collide, what will happen? So textbook only tells collision, collision due to collision, spectral broadening happens. How it happens? So when they can exchange energy, right? These electrons, when they try to collide, electron, see, whenever molecules interact, there are only two types of energies, attraction and repulsion. right? Electron, same charges will repel, opposite charge will attract. So electron, when they come close, they repel each other. As a result of this repulsion attraction, there can be variation in the electronic energies. And that can lead to the scattering of energy, which is the broadening part. The more broad means more energy. So spectral broadening is one aspect that you need to consider while measuring the UV absorption. Normally they measure at the half maximum intensity. Full width at the half maximum intensity will tell how much the spectral broadening is happening. The third one is the intensity of the spectral line. How intense it is. The peak is intense or less intense, more intense. Intensity is governed by three things. One is called how probably is your transition probability, Boltzmann distribution, path length of the sample. So transition probability means in the absorption and emission that we talked about, right? We are talking now about absorption. These absorptions are governed by certain rules. Some absorptions are allowed, some are forbidden. That is due to a set of rules based on symmetry, based on spin of the electron. There are many other aspects. Some transitions are allowed. So those allowed transitions will have more intensity. And you can actually calculate by calculating something called oscillator strength, how much these oscillations, electromagnetic interaction with the electron, and which is leading to this jumping from lower to the higher, how much probability is. Based on that calculation, we can say calculate the transition probability. If the probability is high, you get an intense peak. If probability is less, you get a less intense peak. Boltzmann distribution is a kind of a number of species in the excited stage to number of species in the ground stage, and how that is connected with the energy gap. So energy gap is more. Certain cases energy gap may be more. Certain case energy gap will be less. Whether that has an impact on the distribution of this species in the ground and the excited state as a function of temperature. So Boltzmann come up with a distribution rule that also affects the intensity of the lines, spectral line. The last one is path length. Path length means what? Path length is the length of this, basically the container where the beam is traveling. The length of the beam that travels through the sample, that's called path length. Suppose path length is high, how it affects the intensity of the absorption or intensity of the transmitted light. That is where something that you might have already learned, Beer-Lambert law, which governed the absorption part, which essentially tell you that path length and the intensity of the outgoing light has a inverse exponential relation, which means as the path length is increasing, the transmitted light will decrease. The intensity of the transmitted light will decrease exponentially. You can see e to the power of minus epsilon CL. L is the path length. Same rule is for concentration. So relation between the ratio of the intensity of the outgoing light to the incoming light, how it is related to the concentration and the length, that rule is called Beer-Lambert's law. So many of these absorption techniques are governed by this fundamental rule called Beer-Lambert's law. Okay. Now, this is all about solution. Suppose you want to measure absorptions of solids. Then the technique is called diffuse reflectance spectroscopy, DRS. You have solid sample, you want to measure the absorption. Now the problem is solids will not allow light to go through that. So you cannot measure transmittance. So without getting transmittance, how do you measure absorbance? So what happened to the light when it falls on solid? It will reflect. So now the second question is, can you measure the reflected light and get some information about absorbed light? Earlier, we were measuring the transmitted light and then get some information about the absorbed light. Here, because it is not transmitting, it only reflects. So we collect the reflected light and come to know how much information we can get from the absorbed light. So this is mostly used for powder samples, semiconductors. Wherever there is an irregular surface, we can use this kind of a spectroscopy to find out absorption. Now, when we talk about reflectance, there are two different types of reflections. One is called specular reflection, another one is called diffuse reflection. The pictures will show you what is the difference. Yeah, one looks like the angle of incidence and the angle of reflection are equal. If you can draw a normal here, for every incident beam and the reflected beam, those angles are equal. But whereas diffuse means it's all scattered. So in DRS, what you are actually measuring is diffuse reflection. Okay, because specular reflectance are actually on the surface. Suppose the light beams fall on the surface, slightly enter into the matter as a refraction process, go through the matter, come out from the matter. During that process, absorption can happen. So this coming out light will hit many other particles and then get scattered or diffused. So only those diffused light is what we need to measure. So it's very important that if you are using DRS, you should not use very smooth sample. Some irregular structure is what we need for DRS. So assume that you are getting diffuse. But one problem with the DRS is only some 20% of the energy of the incident beam is reaching your detector. Because of the diffusion, it gets scattered. So you need a very high sensitive detector in DRS. That's one of the reasons why DRS is not as popular as UV visible absorption spectroscopy. So most of the studies we do with absorption is based on transmittance, not based on reflectance. So there is two types of reflection even in the diffuse case, and most of the people work on this Kubelka-Munk reflection. I'll tell you what is Kubelka-Munk reflection in a minute. So the idea is that if the source beam interacts more intimately with the sample by undergoing multiple reflection, it stands to reason that more absorption by the sample will occur. So it has to enter into the matter, refraction, it has to come out, hit wherever the irregular particles are there, wherever absorption can happen, more time it interacts, better. So that more absorption will happen, the remaining light will get scattered, and that diffused light is what you are measuring. Now, these two equations will basically compare these two approaches. T, which is the transmittance based light absorption measurement, which we have seen in the case of UV. T is equal to I by I0. I is the intensity of the light outgoing, transmitted light. I0 is the intensity of the incoming light. So it's about reflectance also. R infinity, where infinity, imagine that the thickness of the sample is infinity, not a single photon is getting. R infinity is equal to J by I0. What is J? J is the intensity collected by the detector. So if infinity is generally 1, that is a hypothetical or theoretical concept of total is collected by the detector. So for measurement, what they do is they use some kind of a sample as a reference where the end is getting reflected. So some barium sulfate or some kind of powder, they will coat it and use it as a standard. Then you use your sample. The concept is that if the reflectance is low, absorption is high. If the reflectance is high, absorption is low. That is general common sense, right? Now, what they did is from the reflectance, the R infinity, which is the absolute remittance of the collected by the detector, this Kubelka and Munk, they developed an equation which is looking similar to what you see in the Beer-Lambert's law. So this FR is not actually reflectance, it is a function of reflectance. Okay, so it's a mathematical model based on which they say that this function of reflectance is equal to concentration divided by scattering intensity. So this is something similar to absorption, Beer-Lambert's law, where this absorbance is equal to epsilon CL. So something similar you can see in Kubelka-Munk curve. This FR is the one that you need to calculate. If you are measuring the reflectance, you can plot it as a wavelength. you may get something similar kind of a spectrum where you can see that reflectance is low, which means absorption is high. Reflectance is high means absorption is low. That's the way you need to interpret the DRS spectrum. Suppose this reflectance, which is R, you can use that reflectance and convert into FR, which is a function of reflectance. Then the same spectrum will look like this. This is like a absorption spectrum. So if you are measuring a solid sample and if you want to generate an absorption like spectrum, what you are supposed to do is you need to plot FR versus wavelength. You get an absorption, and wherever more absorption is happening, you get a similar kind of a peak, as if like in a transmittant based measurement. There is one more application which is called torque plot. Torque plot is for those who work in semiconductors. So this is the relation between the energy of this light absorbed, alpha h nu to the power of n, which is equal to A into h nu by minus Eg. H nu is the light energy, A is a constant, Eg is the band gap. So when you talk about molecules, you talk about HOMO-LUMO, highest occupied molecular orbital, lowest unoccupied molecular orbital. If you talk about solid samples, semiconductors, you talk about band gap, conduction band, valence band, same concept. Okay, so to measure the band gap, you can actually use DRS spectra. What you do is, instead of this alpha h nu, you need to put FR h nu. FR is the Km constant or Km function, Kubel-K-Munk function. So FR you can measure from reflectance spectra. H nu is that you know. N is a number which depends upon the kind of electronic transition. It's slightly complicated. It depends upon the lattice vibrations. It's called phonons, whether the electronic transition is connected or coupled with the phonon transition. It's a slightly complicated topic, but depends upon that you get a number here. If you know this information, you can get FR from DRS. You can use FR h nu to the power of n versus h nu. You get a plot. If you take the y-intercept means x is, it's an x-intercept. X-intercept y is equal to 0. So y is 0 means h nu is equal to Eg. You are plotting h nu here. The cutting point which represent the Eg, which is the energy gap, semiconductor energy gap. So torque plot is used to find out the band gap of the material. So if you want to find out, you are working on something to find out the band gap, what you should do is find out a torque plot, and DRS can be used to measure the or to find out the torque plot. So the two different types of measuring absorption, one is based on transmittance, one is based on reflectance. These are the generally two approaches for measuring absorption. So once it absorbs, the electron is in the excited state. Then the possibility is that it has to come down by giving out energy, right? So what way this can give out energy? It's only two ways. One is radiation, another one is non-radiation. So most of the time, in the case of UV and visible region, it comes out in the form of radiation. Whereas in other case, IR, radio waves, or in gamma ray, or in microwave, it comes not as a photon. So it's very interesting. In the entire spectroscopy, if you talk about, only for UV visible, this energy is dissipated as photons. All other cases, energy is dissipated as heat. Okay. So now luckily for us, UV visible, this coming down from the higher energy levels to the lower energy levels is in the form of light. So this person, his name is Alexander Jablonski, is a Polish person. His contribution to this particular field is very interesting. He used to, what I heard that from the biography of Alexander Jablonski, that he used to participate in World War I, World War II, because in Polish Russia, those regions, military service is compulsory. Whether you are a scientist or a civil, normal human being, doesn't matter. You have to go to the army. So he used to participate in World War I, World War II, got arrested, put in jail. But the remaining time, he did some science also. which is very valuable. Now, almost every field, irrespective of just fluorescence spectroscopy people, many people use his diagram, which is called Jablonski diagram. Jablonski diagram is very well-known diagram which talks about what happened to this electron after excitation. It's a photophysical processes. So they give some terminologies like S0, S1, S2, T1, T2 kind of thing. Talks about S stands for singlet, T stands for triplet. It talks about the spin state of the electron. Electron has up spin and down spin, right? So what will be the spin of the state in that molecular system before light excitation, after light excitation? That's called the representation by S and T. So S0 talk about the ground state, which is a single state. That means spin, there is only one way of arranging the spin. What is the ground state arrangement? One up spin and one down spin. That's the only way you can arrange it, right? So now it absorbs the light, it jumps to the first excited state, which is also a singlet S1. That means one electron is up, one electron is down. So then what's the difference between ground state and up excited state? Ground state also it was up and down. The difference is that one of the electrons get more energy from the light. So what happens? Then there is an orbital separation between these two electrons. S orbital can go to p orbital. So one electron jumps orbitally, but the spins are still opposite. Okay, that kind of a situation is in S1. It can go to S2, S3 like that. Depends upon how much energy you are pumping. From S1, it can come back to S0. All that it should use is it gives out the energy. It just gives out the energy in the form of a light and comes down. That is called fluorescence. While it is in S1, where orbital is separated, it can undergo flip change. It can flip the spin, right, in the excited state. Such a flip change happens, then you can see there is another state which is called triplet, which essentially means that this spin state now you can arrange in three different ways. What are those three different ways? The spins are both up, that is one way. Or it can be both down, second way. What is the third way? Triplet. That means three different way of arranging spins. One is this, one is this, one is this, the third one. Typical PhD question that when we come for PhD interview, we ask these kind of questions. Because it's confusing, right? Up and down is singlet, no. That's not triplet. Up and down means it is a single state. Triplet means it has to be same orientation. So this is confusing. The answer is the third state is a superimposed state of these other two. Okay. So basically there will be three different ways of arranging the spin state, the same energy. That's why one line is a triplet energy. Now from this also it can emit light coming back to the ground state. From singlet emission it is called fluorescence. From triplet it is called phosphorescence. So these are the two ways the light can come back to the ground state, fluorescence and phosphorescence. Now all these involves kind of a time scale, different time scales. Absorption is the fastest process. It happens in femtoseconds, right? This battery is low. Battery low. So absorption is the fastest process, happens in femtosecond, fluorescence in nanoseconds, phosphorescence in milliseconds. In between, wherever you are seeing some kind of a wavy lines, there are processes that is happening from or within the excited states. You can have energy loss in the form of from S1 to T1. That's again called intersystem crossing. These are all energy dissipating pathways in the form of heat. Now, once it reaches all these processes, basically explains after the light absorption what happens to the electron. They're called photophysical processes. And one major study about photophysics is understanding the dynamics or the kinetics of these processes. Can you do the next slide? Yeah. So again, some terminologies that we need to talk about in fluorescence is, one is called Stock shift. See, you measure absorption. For example, Birlambert's law that we just see. You measure the absorbance, that's on the left hand peak. You measure the emission, which is fluorescence. Now you see that the maximum lambda of absorption and emission, there is a gap. Emission is always red shifted. What could be the reason for that? Here? Why it is coming in higher wavelength? Energy loss is happening. That is actually evident from the previous spectrum. If you can go back to the previous slide, actually it shows that some energy loss is happening in the form of heat after light absorption. You need to look at the can you go back to the previous slide? Look at the process in carefully. See, after the light absorption, there is a fast process. This time scale is 10 to the power of minus 12 to minus 10 seconds, whereas this is minus 10 to minus 7. So this process is a faster process than this one. So that can compete. That means that happens first. It excites, loses some energy, then only it is emitting. That is the reason why this be always red shifted compared to the absorption. Some energy is lost. Next slide. So that shift is called stock shift. Okay. Another one is a famous person, Michael Kasha. Michael Kasha suggested that emission, this is general principle, there is an exceptional case, emission is independent of excitation, which means you have this, wherever this region, this entire region, the sample is absorbing, right? You can excite here, 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 here. All region sample absorbs. So you excite anywhere in that region, you will get the same emission spectra. That is called Kasha's rule. Emission is independent of excitation. Why that happens? Again, Jablonski diagram will give you the answer. You can excite up to any wavelength, but emission is always happening from S1. Right? So, because emission is happening at certain point, irrespective of your excitation, this emission spectra will look similar irrespective of where you are exciting. That rule is called Kasha's rule. Third one is called mirror image rule. This is also general principle. All compounds may not exhibit. Mirror image rule says that your absorption and emission, absorption fluorescence, it will be looking like a mirror image to each other. Right? What are the peaks? The other peaks. Energy only is varying. Energy of absorption, energy of emission is different, but there is a intensity mirroring happening between absorption and emission. The reason is all those absorption that you are seeing in the Jablonski diagrams from one electronic state to another electronic state involves vibrational energies also. There are small lines that you must have noticed in between the electronic energies. So these vibrational energy levels which are embedded in the electronic energy, the probability of transition between absorption of two vibrational is the same as probability of emission between those lines. So there is a 0 to 3 absorption, 0 to 3. If you calculate the probability of that absorption, that will be equal to the 0 to 3 emission. So there is a one-to-one probability correspondence between the absorption and the emission in an electronic excitation due to the involvement of vibrational levels. So that's why there is a mirror image principle. Next, sir. A few minutes we'll spend about the dynamics part. See, in chemical kinetics, you know rate of an equation. What is rate of a chemical process? Some rate constant into concentration. That is a normal way that chemical kinetics will teach you. Rate is equal to K into concentration. The only difference here is in photo-initiated process, the rate of that process will be not depending upon the concentration. That's an interesting element to note in photo-initiated chemical reactions. Doesn't matter whether you're taking 500 grams, 1 kilogram, 2 kilogram. It doesn't depend upon the reaction rate. Whereas in normal reaction, it depends. Initial concentration, right? A0 that you are using in the calculation. But in light induced, it is not. Because light induced depends upon how much light intensity is absorbed. That is the one that decides the rate. So, rate of a reaction is proportional to IA, not concentration, which you can equate by a proportionality constant phi, which is called quantum yield of that reaction. Right? Quantum yield basically is an efficiency parameter. Quantum yield is representing the rate constant in your normal chemical kinetics. See, normal chemical kinetics, this equation is rate is equal to K into concentration. Here it is rate is equal to phi into IA. So this is the major difference between the dynamics of a normal chemical kinetics to an excited state kinetics. Now, if you want to use a particular instrument called steady state fluorescence spectrometer, you must have heard about steady state fluorescence. Steady state fluorescence means you have a lamp to excite your sample. You keep on exciting. So S0 goes to S1. It starts emitting. It is undergoing non-radiative processes. And after some time, this concentration of S1 becomes steady. That is called steady state concentration, right? So under that conditions, what happened to the concentration of the S1? It becomes steady. That means the rate of change of concentration of S1 becomes 0. ds by dt is equal to 0. Now, if you want to find out that concentration, which is steady in concentration, what you need to do is the rate of formation of S1, you can equate to the rate of decay of S1. How rate of formation of S1? It all depends upon IA. If phi is 1, that means every photon falling is absorbed. Rate is equal to IA. So formation is IA. How it is decaying? Decaying through, there is one emission decay process, there is a non-radiative process, there is another non-radiative process. So Kf plus KIC plus KIC into concentration. So if you can equate these two things, then the steady state concentration of S1 can be obtained as IA by the sigma K. There is one way to find out how much concentration of the excited state you are generating in a steady state fluorescence. Next. Another important aspect about fluorescence spectroscopy is the lifetime. It's called excited state lifetime, which is called normally termed as tau. See, the definition of tau, that's another interesting aspect. It says average time a molecule excites in the excited state. Why this term average? See, you excite some molecules. For example, some 1 mole of anthracene, you excite. Anthracene is a chemical. Goes to excited state. After 5 nanoseconds, it comes down. So 5 nanoseconds is the time that all the 1 mole of anthracene stays there. But that definition is not applicable. Is the average time the anthracene molecule stays in the excited state. That is called 5 nanoseconds. So why there is an average time proposed? Or the definition of the excited state is when the intensity becomes 1 by E of the initial intensity. That is another definition. So all these things leads to a particular fact that emission is a spontaneous process, which means if you excite 1 mole of anthracene or any chemical species, the electrons will come from S1 to S by purely probabilistic fashion. You cannot control it. So after excitation, time T0, whatever the measurement, so that's why the reason excited state is a average lifetime. So lifetime and the rate constant are inversely connected. So if you can measure the rate constants, you can find out the lifetime of that species in the excited state. So if fluorescence lifetime you can calculate. This is called fluorescence quenching. So for sensing application, those who are doing research in sensing part, fluorescence spectroscopy can be widely used for sensing toxic or unwanted species, any kind of analytes. So the question is how this happens. Quenching is happening. Quenching is basically decrease the intensity of the fluorescence emission. In the absence of any external species, your quantum yield of fluorescence can be expressed as a ratio of the rate constant of fluorescence from sigma k by sigma k. Whereas in presence of quencher, the quencher interact with your fluorophore in the excited state. So an additional component will get, which is called KQQ, which is the bimolecular interaction between the quencher and the fluorophore. If you take the ratio of these two quantum yields, you will get a very simple equation like y is equal to mx plus c, kind of a straight line equation. Phi 0f by phi f is equal to 1 plus kq tau q, which essentially means that, next slide, go to the next slide. Yeah, so before. By measuring the quantum yield or the efficiency of that emission process in the presence and absence of an external species, you can get a straight line equation which is called Steinheimer equation. Experimentally, what you should do is you measure the emission intensity, presence and absence of a analyte or a quencher, and you increase the concentration of that quencher. You get a straight line. From the slope, you can actually calculate this KQ. KQ is the quenching constant. That means how effectively the external species is decreasing the intensity of the fluorophore. So we can quantitatively measure the impact of an external substance on the emission quenching process. That is the idea of a Steinheimer plot. Now, remaining 5 minutes, can you go a bit more? Next slide. Next. I just want to talk about this topic, which is a kind of a research topic. It's called transient absorption. You don't have okay. Transient absorption. So we talk about absorption spectroscopy. We talk about emission spectroscopy. This is called transient absorption. Transient absorption is also known as pump probe technique. See, so far what we have discussed is there is a sample, there is a detector, there is a light source. Now, the only difference in this pump probe is there are two light sources. Okay, one light source is going to pump the sample from the ground state to the excited state. It's called pump light. Then when it is in the excited state, in the S1 state, another light is coming. That is called probe light. So while this is in the S1 state, the probe light will come through the sample, which the sample can again absorb. So what you are essentially measuring, can you go to the next slide? It's not working. One more. So what you are measuring is, you have the ground state species, you use a light, it excites the excited state. While the species in the excited state, another light is coming. So this species in the excited state will further absorb. So in pump probe technique, what you are measuring is excited state absorption. It's called transient absorption. So there's a powerful technique which is called transient absorption spectrum. If you are doing research in excited state chemistry, transient absorption spectroscopy is a very powerful tool to see how a species which is already excited can further absorb light. It's like a second absorption. So that absorption can also be monitored, measured, which is happening actually in what kind of time scale? Can you give some kind of a time scale for excited state absorption? Because you have seen the Jablonski diagram, the kind of time scale 10 to the power of minus 11, minus 12, minus 9 of a second, right? So this pump probe technique is even going to below that, 10 to the power of minus 12 second, which is pico, 10 to the power of minus 15, which is femto. So within that short time, the process happens, absorption or emission, transient absorption, transient emission. Those things can also be monitored by this powerful method called transient absorption. So we don't have time to discuss in detail, but those who are interested in measuring the excited state absorption, you can see how to use this pump probe technique to monitor your excited state absorption. So next, can you go to the last slide? Next. So what we are trying to communicate to you is, it's a very exciting area of research, light matter interaction. Understanding the fundamentals of absorption and emission is essential to do research at a molecular level, because all these, we can use instruments, but without understanding how a molecule interact with a photon, many of these application part you may not be able to actually carry out. Fluorescence spectroscopy has a wide variety of applications, and the two important things is very high sensitive technique, so you need only small amount. So in my lab, people use 10 to the power of minus 6 molar solutions, 10 to the power of minus 10 molar solutions. You don't need much sample. That is one advantage. And it's a non-destructive method. You get the sample back. Nothing will happen. Most of the samples are not photo bleaching. So because of these two attractive things, you can also, because it is highly sensitive, you can detect, analyze in parts per million, parts per billion concentration. Very small concentration you can work to sense some of these things. So with this note, let us wind up because time is up. And if you have any kind of queries, questions, please ask for the next 2-3 minutes. Anything that comes to your mind, because the audience is so wide, I can understand it's not from alone fluorescence part or chemistry part. But any general questions, please interact.
Participants, if you have any queries, please.
Yeah.
What kind of sample nature?
Yeah, so all possible. All 3 states are possible. Most of the things people do solution state. That's easy to handle.
Is there a solid version for
Solid waste also is there, because if you do look at that instrument layout which we did not discuss, we collect fluorescence from the 90-degree angle. So you can use solid state, solution state, gas state, thin films, gels. Yes.
If you are taking a UV of the extract or any synthesized compound, what should be the concentration so that?
That's a good question. See, UV absorption is governed by a particular law called Beer-Lambert's law. Beer-Lambert's law defines absorbance, which is log of ratio of the intensity of the light. Absorbance, if it is equal to 2, a number 2 means 99.99% of the light is absorbed by the sample. That means detector is not getting any transmitted light. Dilute the sample again. Otherwise, whatever measurement that you dilute the sample again. Otherwise, whatever measurement that you are doing may not be accurate. Toxicity, 50 value separately, and then see how much amount. If you want to see, you can do a UV visible spectrophotometer to measure the concentration, because absorbance and concentrations are directly proportional. So you can measure the absorbance over a range of concentration or even one particular concentration and see the corresponding, measure the absorbance, you can back calculate the concentration in that sample. That way you can say that this sample contains this much, so it may be toxic. But toxicity as such, you need to do other studies, assay studies to find out the toxicity part. But UV can assist there. Yeah, after that. Okay.
why is that intersystem process?
Okay. The only difference, so first question is why in the system crossing is happening. See, excited state is a high energy state. Any system which is high energy, try to dissipate the energy to come to the ground state. So the system is looking for channels, how to dissipate energy. Inter-system crossing is one channel where the energy can be decreased. It can. These are all happening simultaneously. Imagine a glass tumbler, put some water, make some holes. Through all holes, water will come out. The Jablonski diagram is like that. It's happening simultaneously. Only thing is that some holes are big, some are small. So the amount or the rate at which flow happens is different. Probability will be varied. Okay, depends upon many other factors, but these are all processes happening simultaneously. So inter-system crossing is to reduce the energy. Now, what is the difference between singlet and triplet? Singlet is the spin state will be always opposite. Triplet, it is always parallel. That's only difference. Yeah, inter-system crossing is happening because Pauli's exclusion principle say that it has to be up and down. So up and down means it can come close. When it comes close, what happens? Repulsion energy increases. So this is a high energy stage. Whereas this state, they stay apart. So it's a lower energy state. That's why spin flip happens. Last.
Sir, suppose we have synthesized any material and we have taken suppose we are adding material for detecting something
Okay.
like metal or something,
Hmm.
then the peak will pinch.
Ah.
In that case,
Right.
it will pinch.
Right.
I want to ask this
Yeah, the fluorescence. Yeah. So generally, what happens is that initially you will